Welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but still want to be its friend. I'm your host. I'm Dr. Moiya McTier. I'm an astrophysicist, a folklorist, and a really good friend to the universe. It came to my third birthday party. And today I'm expecting my first return guest, which is very exciting. But this will be his first time in my office. So I'm expecting to be joined by Chris Allen, who's a comedian, and I loved making the Dark Matter episode with him. So I wanted to invite him back to talk about dark energy, and he should be here any minute now. Chris, come on in. Welcome.
Hey, how you doing, Dr. Moiya?
Great. It's really good to see you again. How are you enjoying your time here on campus?
I love it. It's a beautiful campus, and what an office.
Right. You can tell I like cozy things.
Yes.
I like it smells of leather and rich mahogany in here. Is that how it goes?
Oh, yes. This is definitely Ivy League over here. This is fantastic. I love it. It fits everything.
It does, yeah.
I love it here.
Yeah, so let's sit down, let's get comfortable and catch up. It's been a while. Do you have any news or updates since we last talked?
It's just been going well. My comedy special's been doing well. I'm still fascinated with the universe. And I will say one interesting thing. I had a hard opinion on gas giants, and I have since changed it.
Oh, can you tell me what was your opinion and how has it changed?
I know it sounds silly, but I used to not respect gas giants because they didn't have a hard surface. And I was like, in my book, I was like, that doesn't qualify as a planet. But then I did some research and I looked up all the criterion. And I was like, oh, okay, it is a planet. And then I looked at it a little further and I'm like, you know what? I kind of relate to gas giants a little bit more because like you can see them, you know that they're there, but you can't land on them. You can't get too close to them. And I'm like, that's kind of like an introverted person.
Yeah.
Like you want to be part of the group, but you don't really want to be bothered. And I was like, I can really relate to like a planet like that. It's just like, you can come see me, but you can't come in. You know what I mean?
Ooh,
I like
yeah.
that idea. We're going to have these gas giants that like, look, I love being a human being, but I know once we start going to these other planets, we're really just going to tear them apart. Let's be honest. We're going to tear them apart, just like we did our own planet. So just knowing that these gas giants won't be able to be taken advantage of, it makes me feel pretty good.
Oh, you're so right. I love the comparison of them to an introverted person because it also... like when you go deeper into a gas giant planet, there is, we think, like a very small icy or rocky core at the very center. So it's like with an introverted person, you really have to dig deep to get to the core of who they are.
And if you get close, like the pressure is just going to crush you before you can even get there.
Yes. Yeah, you know, if you really want to get to know that introvert at the party in the corner, you have to go through layers of liquid metallic hydrogen and all of those lightning rounds in the upper atmosphere. They're not going to make it easy for you.
Yeah.
Chris, I'm telling you right now, if you ever have a space question to help with a joke that you're writing, please reach out. I would love to help with that. Yeah,
okay.
100% serious.
All right, you be my space ghostwriter. All right.
Yes, please. Awesome.
All right.
So last time we met, we did a little prelim exam, a get-to-know-you questionnaire. I have since come up with a few new questions, and I'd love to hear your answers to those.
Okay.
Awesome. Do you have a favorite unit of measurement?
Oh, that's a great one. You know what? I like to call things furlongs. I don't even know what a furlong is. It's just fun to say.
It is.
It's fun.
You're reaching back. You're going back in time. Yeah. Is that a unit of distance? Like you walk furlongs?
I'm not sure.
Oh, then let's do a live Google.
Is it nautical? Is a furlong? Because for a while, can I admit this? This is a nerdy podcast. I was obsessed with Tolkien and like Lord of the Rings for quite a while, and I might have heard it on there. I'm not sure. It might be a nautical term. Actually, I guess I can look it up too.
I just looked it up. It's 1/8 of a mile or 220 yards.
Really? So what was the point of that one?
I don't know. Apparently it's used in the Bible.
Oh, okay. Maybe that's where I heard it at church.
Yeah, so it's old.
A furlong.
I like that. That's perfect. You just like pulled that out of the... Yeah. Was it the recesses of your memory or was it right at the top there?
It was I was in the military and I had a pretty nerdy job. So we used to always kind of mess around with each other with stuff like that. Like, oh, instead of give me 2 feet, give me a furlong. It's like, what are you talking about? We would cut wires and stuff like that. And we would just mess with each other and come up with all these, just bring up these old, ways to measure things. I know that's a very specific reference, but yeah, that's why.
Yeah.
A furlong.
That's perfect. Next, you're going to be talking about like leagues and I don't know.
Leagues
I
under the
can't
sea.
think of any more.
Yeah.
Those are the only old-timey distance measurements I can think of.
Yeah. I don't like inches, though. I really do feel like we should just go with everybody else.
Yeah, move to the metric system.
Yeah.
Base 10
it makes
so much more
sense. It makes sense.
Yeah, I agree. As a scientist, I agree.
What is your favorite?
Ooh, it changes every day. There's a beautiful unit in radio astronomy called the Jansky, and it's only useful for radio astronomy because they deal with such faint signals. It's a measure of flux density, so how much energy is flowing through your instrument per second. And Jansky is like a really, really tiny measurement that other fields find completely useless because they would have to measure in the billions of Janskys. But for astronomy, it's like, we have 10 Janskys.
Oh, and is that like a signal strength in the return?
Yeah.
Oh, okay.
Yeah, it's like the signal strength for whatever you're observing. And for a lot of radio signals, the strength is really weak.
Oh, yeah,
so your signal to
course.
noise ratio is really low. And Jansky's tells you like how far above the noise does your signal go.
Right. I was a radar maintenance technician in the military for about 6 years. So yeah, I'm somewhat familiar with radio waves and propagation and signals and all that kind of stuff.
Well, that actually leads perfectly into my next question, which is, if you could see in a different part of the electromagnetic spectrum, so like in a different wavelength of light, which region would you choose?
Probably infrared.
Why?
Predator.
You're like, I want that night vision,
Yeah,
baby.
I don't know. That would be cool. I recently thought about that too, how limited our perception is in our world because there's so much more going on and in the light spectrum and sounds and all that kind of stuff. And we just see a very small portion of it. It would be, could you imagine just being able to see or hear that stuff? It would be so overwhelming.
Yeah, you'd see the universe in literally a new light.
Yeah.
With infrared, you'd be able to see a lot of the dust in the Milky Way. So when we look to the center of the Milky Way, where the big black hole is, it's really hard to see it because there's so much dust in the way. So we have to look in the infrared because the dust absorbs other types of electromagnetic light, and then it re-emits it as heat, which we see in the infrared. So you would just see so many details that we can't see with our eyes.
Yeah. It would be scary. I can turn it off and on though, right? Or do I have to see in it?
Ooh.
Okay.
Let's say yes.
All right.
Let's say it's a voluntary thing.
All right. Yeah. Yeah. These are interesting questions.
Oh, good. I'm glad. Yeah, I thought of the measurement one because I was dealing with some unit conversions from metric to whatever we have here in the United States. And then I wanted to know if other people had strong opinions. Yeah,
that was one, when I took math, that was one of the weirdest sections and it was so confusing for me. Like my teachers would make us convert, like turn feet into seconds or turn seconds into miles per hour. And you have to go through all these different steps to convert time to a distance and then the distance to, it was pretty interesting. But that was so confusing to me. I was like, why are we doing this? But looking back, pretty fun. Now I look back, it's fun stuff.
Yeah, very fun. I do wish that they taught it in a more practical, applied way, though, because there are so many people who are like, when am I ever going to use this? And they will, but you don't learn it in a way that makes it clear how you'll use it.
Right, like money or whatever. Like I try to relate things to coding for my son. But yeah, I think most adults, if you try to break it down into money, that makes sense.
Yeah, good idea. All right. Well, thank you for answering those extra questions.
No problem.
I want to jump into dark energy, which, as we discussed last time, is different from dark matter, but we didn't get into the energy of it all. So first, I'd like to know what you remember from our dark matter episode, and if you remember how it's different from dark energy.
Dark matter is everything else that the universe is made up of, all the stuff we don't see. I'm guessing. Yeah. All the space. Yeah, well, it's not all the space, but it is
It is very present in space, but it's all of the physical matter that we just can't see. So it's there, it has gravity, but it's not shining like a star.
Oh, okay. I guess I just explained it extremely wrong, but okay.
No, you're
So
good.
I'm guessing the energy would be probably based on the interactions or the decay that happens between those bodies and the energy that it either releases or absorbs.
Ooh.
No?
That's honestly a better definition for dark energy than what we have. That would make more sense because we do know that things are decaying out there. There's radioactive decay that's taking particles and then disintegrating them into smaller particles. Dark energy isn't related to that.
Oh, okay.
But we've just named it terribly. Just like, remember how we talked about transparent matter and invisible matter instead of calling it dark matter?
Right.
The name with dark energy is also pretty trash because we just called it dark since we didn't understand it. And honestly, we know even less about dark energy than we do about dark matter, which is unfortunate. Yeah. So the biggest difference between the two is that dark matter is stuff. It's substance that takes up space, but we can't see it. So we can only study its gravitational influence on other things. Dark energy is something else entirely. It's not matter. So it's not stuff that you could like hold or touch or interact with gravitationally. It seems to be this type of energetic force out in the universe, and we can see kind of what it does, but we can't observe it directly. We can even less than we can observe dark matter, right? Like dark energy is just super mysterious.
So we can see the results of what it's done, but not it doing it.
Yes, exactly. Like even when we go out and we try to map dark matter, we can't see it, but we have other methods of finding its outline. Right? Like we can use gravity to determine its outline. But dark energy doesn't even work with gravity like that. It doesn't have an effect that we can use to trace its boundaries. All we can do is see how has it changed the universe over time. And so that makes it really hard to study. Like when you're trying to study something and you can't even define what it is, that's really hard. Like imagine you had never learned about Earth's atmosphere.
Right.
And you were trying to figure out what air is, but you don't know about atoms. You don't know about gas. It's just like around you and you move through it, but it's so hard to study if you don't have that fundamental information.
So how do you study stuff like, because I find it fascinating, and I know there's people all around the world studying this stuff. Like, where do you even begin?
Yeah. So we are studying it right now, and it's kind of a newer field. We didn't know about dark energy until the 1990s. So it's only in the last 30 years or so that we have started studying it, and I'll get to those methods at the kind of end of the episode.
Okay.
But I want to discuss the history first. Like, how did we realize it was there in the first place? So we're going all the way back to the 19-teens. We're going back over 100 years. In the 19-teens, people thought that the universe was static, that it was staying still, not getting bigger or smaller. Does that make intuitive sense to you?
I can understand why people would think that. It makes sense.
Yeah. Einstein was convinced that the universe was still. Actually, when he created some of his big famous equations describing the shape of the universe, he added in this weird, it was a Greek letter lambda, this lambda term that he called the cosmological constant, because his observations of the universe or his thought experiments about the universe weren't matching up with his idea that it should be still. So he added in this extra component, this extra constant factor in the equation that would just adjust for that difference. And it turned out that perfectly explains the expansion of the universe. So all of that is to say that even in the 19-teens, when we thought the universe was still, that theory wasn't perfect. There were holes in it, and people were trying to patch those up. all the way back then, we knew that the Milky Way was made of stars and gas. And we saw that in the 1600s when Galileo looked up at the Milky Way with his telescope for the first time, and he saw individual specks of light. So we knew the Milky Way was made of stars. And we had identified other little nebulae, these cloud-like objects like Andromeda and the large and small Magellanic Clouds. So we knew that there were these other little fuzzy universes out there. We called them island universes. And there was this huge debate in the astronomy field. There were these two names that were going against each other. One was Heber Curtis. He used novae, so that not supernovae, but just tiny little stellar explosions to estimate the distance to Andromeda, which at the time we called the Andromeda Nebula. And Heber Curtis estimated that Andromeda was about 50,000 light years away from us. Do you have any sense for like how big the Milky Way is?
No, I know it's massive, but I have no idea how big our galaxy really is.
Mm-hmm. Well, they didn't back then either. They were like, 50,000 light years, that's huge. That must be bigger than the Milky Way. Or at least that's what Heber Curtis assumed. Because they thought that the Milky Way was like big, but they didn't know how big. The other scientist involved in the debate was Harlow Shapley, and he was convinced that the Milky Way was actually much bigger than 50,000 light years. So, of course, that Andromeda Nebula is a part of the Milky Way. And it turns out that they were both wrong and right. Andromeda is outside of the Milky Way, but it's 2.5 million light years away, not just 50.
Okay.
So it's a lot further than we expected. And Harlow Shapley was right that the Milky Way is much larger than 50,000 light years, but it wasn't large enough to extend all the way to Andromeda. So, they both got little pieces of it right.
Man, that is insane. That's when you really think about that time. That's crazy.
Right? Just really picture the 19 teens, all those big poofy dresses, all those suits. Yeah. All those walking sticks, like, what a time.
Would you say that, can you give them any credit for what they came up with at the time? I mean, they were pretty off, but at the time, even to have that concept is pretty wild.
Yeah, I agree. Like, even to be able to estimate the distance to Andromeda, like, that's a huge deal. They were using new technology at the time. They were using early forms of spectroscopy, which is when you take light and you split it up into all of its different wavelengths and measure how strong it is at all of those wavelengths. That was invented in the 1800s. So they're really cutting edge back then.
So they had to be so smart. I can't imagine what they would figure out with the equipment and things that we have nowadays. That's wild.
I actually used to get into this debate with my PhD advisor in grad school. Are scientists now smarter or as smart or less smart than scientists in the past?
Ooh.
And I think we're as smart. I agree that what they were doing was very impressive, but if they were alive now and they had learned this stuff in high school or college like we do today, then that would be their starting point, and they would use their same smarts to progress us from here. I think that humans, for the last, 10,000 years, have basically been the same level of smart. We've just been starting at different jumping points.
I feel you on that. I totally agree. Because when you look at kids, their level of technology, like my niece, it's like their level of technology baseline, iPhones, touchscreens, they understand AI. Like, are they any smarter? No, it's just their baseline level of knowledge is a lot higher, but they're not smarter, which I find really cool.
I mean, I would love to see them try to navigate a paper filing system.
Oh, yeah. Like the Dewey Decimal System? Yeah.
Yes, give them a card catalog. They would be lost.
They would be lost.
So it really is like we start at different points and people know different things and they forget different things as it's less useful in the society they grew up in. So, yeah, it is fun to think about what a smart person back 100 years ago would have known.
Yeah, that's pretty wild. Oh, man, 50,000 light years. That's what they thought. And you said it's 2.5 million? God, that is insane. So light traveling 2.5 million years.
Yes.
It's so true. It's astronomical. It really is. It blows your mind. You can't fathom these distances. And It's crazy.
Mm-hmm.
And Andromeda, it's like it's there right now. It's there right now. But I love it. It blows my mind. I love it. Sorry, I'm freaking out.
No, I love it. Please freak out because it is so cool. And Andromeda is the furthest thing we can see. Like our eyes, our tiny little puny eyes that can't even see in the infrared, they can detect photons that traveled, like you said, for 2.5 million years from Andromeda, and that's awesome.
That is awesome. How do we know there's not another planet? There could be somebody in Andromeda right now talking about. And here's the thing, and then we can move on. They might call our galaxy something else, and we call theirs Andromeda. We call ours the Milky Way, and we could be something totally different. Insane. All right.
Isn't it wild to think about?
Wild.
Yeah, like there could be life forms over there that are collecting data just like we are, and they would be able to see the Milky Way and see different stars in it. Like there could be an Andromeda Chris right now asking the same questions.
What's up, Andromeda Chris? I might have to use that name on something. I like that.
Ooh.
All right.
Yes.
Sorry. God, I love this
No, you're good. Okay, so that's the 19-teens. Okay. And in that same decade, a few new methods are developed. One of those methods is by Henrietta Swan Leavitt, who figures out how to use a special type of star called a Cepheid variable to measure pretty accurate distances out in space. I did a whole episode on Henrietta Swan Leavitt, so go check that out, especially if you want to learn more about this relationship. But basically how it works is these Cepheid stars, they pulse. They get brighter and dimmer over time in a regular periodic fashion. And Henrietta figured out that if you time how long it takes for the star to do one pulse, that period is related to the intrinsic brightness of that star. And when you know something's intrinsic brightness and you know how bright it looks to you, you can figure out how far away it is. I think that method was developed in like 1917. And it took some time for people to learn about it. So eventually in the 1920s, people were using this method and getting distances to even further objects.
What was her name again?
Henrietta Swan Leavitt. She was a deaf astronomer who worked with a group of women who were running calculations on data. And she really helped us understand like how distant parts of the universe work.
That's awesome. In 1917, that had to be so tough for a woman,
Yes.
Crazy. Oh, that's so dope. I never knew that. Shout out to her.
Shout out to her.
Yeah.
She was doing amazing work. She was getting paid less than all of the men at the Harvard College Observatory where she worked.
Say.
I know. She was, though, I think getting paid the most of any of the women.
Okay. That's something,
like,
right?
All right. Go off, queen. Sure. So with those new methods, in 1923, a young astronomer, he was kind of fresh off of his PhD, named Edwin Hubble, came along and started using those methods to study distant objects. I see that name sounds familiar.
This is awesome. I'm hearing Hubble's origin story. I've known the name, but I don't really know much about the guy, so this is cool.
Okay, great. Yeah. Edwin Hubble, he was a freshly minted doctor of astronomy, and he was studying Cepheid variables in the Andromeda Nebula, as they called it back then. And he found that the distance to Andromeda was much larger than the distance to the outer stars in the Milky Way. So he kind of settled the debate once and for all in 1923. So when Edwin Hubble finished the debate, that was the first time that the science community understood that the Milky Way is just one of many galaxies out there. We'd had the word galaxy before, but now it took on a new scientific meaning as a collection of stars separate from the Milky Way. So he started studying other galaxies once he defined what they were. And he wasn't just measuring the distances to them, he was also measuring how fast those galaxies are moving through space. This is another thing that we can do with spectra. Are you familiar with red shifting and blue shifting?
As it goes away, it changes one color. I couldn't tell you right now.
Mm-hmm. No, but you're right. You're spot on. As a galaxy or a star or anything moves farther away from us, the light waves that it emits, it takes it takes longer for those light waves to reach us. So it seems like those light waves get stretched out, and we call that redshifting. We can measure how much it redshifts, and that tells us how far away that thing is moving. We call this radial velocity. Okay. And so Edwin Hubble, he had the distances and he had the radial velocities to a bunch of different galaxies out there. And he discovered that the farther away a galaxy is, the faster it's moving away from us. Wow. This was a huge paper in 1929. This was kind of his biggest paper ever. It has more than 1,100 citations if you go and look it up. The paper was called A Relation Between Distance and Radial Velocity Among Extragalactic Nebulae. So very straightforward title, which I love. And
wait, you think that's straightforward?
It tells you exactly what he studied.
To a scientist, that's so straightforward. Read that again. Read that one more time and tell me how straightforward that is.
Okay, sure. A relation between distance and radial velocity among extragalactic nebulae. It tells you the relationship between the two things he studied, which were distance and velocity of these extragalactic sources.
Please, I think if you live in New York City, go outside and ask 4 random people if that's straightforward.
No, you're so right. You are so right.
As a scientist, you're completely correct. Because I'm like, I don't know what it means, but I know what it means. But you were like, so straightforward.
This is why it's good to talk to people outside of academia, because you're right. That's not straightforward. Nebulae. But my sense is just so skewed. Perfect. He wrote this paper with a perfect, very clear title.
Yes, 1,100 citations.
1,100 citations. And in the paper, he showed that most, not all, but most galaxies are moving away from us. And the fact that they're all moving away from us, except for the ones very close by, means something. That means that the universe is expanding. Mm-hmm. Because if the universe were staying still and these galaxies were just moving according to gravity, like being drawn towards each other, you would expect some to be moving away and some to be moving towards us. Mm-hmm. Even if the universe was expanding because it was moving away from some central location, we would expect that some would be moving away and some would be moving towards us, unless we were that central location. Mm. But there's this idea in science that we are not special, and that if we have a conclusion that's based on us being special, that's probably not the simplest, most basic explanation there could be.
Wow. Yeah. Mm-hmm. I like that. Yeah.
So Edwin Hubble looked at that and was like, we're probably not the center of the universe. Actually, other people had mapped the Milky Way and found that we're not the center of the Milky Way, so how can we possibly be the center of the universe? So, ergo, the universe must be expanding. And this was actually in line with the new, at the time, Big Bang Theory, which people kind of landed on around 1927. Mm-hmm. So the Big Bang Theory says that early on, the universe was very, very tiny, and then it expanded rapidly, and it kept getting bigger until it reached its current state. And once we learned that the universe was expanding, we were like, oh, that makes sense. The universe is just it's just keep getting bigger.
Right.
Because there was that energy at the beginning that made it explode. So that was a good confirmation that Edwin Hubble's observations were correct and that the Big Bang Theory was probably right.
He said as things get further, they're going faster.
Yes.
Is that kind of related to relativity? I thought I've heard something like as we get further away, like, so was he kind of like stumbling upon this kind of stuff without realizing it? Like relativity, or am I conflating two different things?
No, that's a good connection to make. Relativity works on smaller scales, so Edwin Hubble wasn't seeing that, not like Einstein's relativity. He was seeing that things move at relative speeds, that things closer to us move relatively slower than things further away from us, but that's not like Einstein's special and general relativity.
Oh, okay. All right. Mm-hmm. Okay.
Good clarifying question. I'm glad you asked. So that thing that he found, that the further away the galaxy is, the faster it's moving, is interesting. that also gives us a clue as to how the expansion of the universe works. Because it's not just that the galaxies are moving away from us through space. Mm-hmm. If that were the case, then you would expect to see all the galaxies kind of moving at the same speed. Like if you're playing a game of tag and you're and you're standing at the center and all of the people, let's say like every human has to run at like 2 miles per hour, right? All of the humans evading you are running at the same speed.
Right.
If you were that tag person and you notice that the people on the outer edge of the game are running away from you faster, that shows you that they are not all traveling at the same speed. Mm-hmm. So what he inferred was that the galaxies themselves are not moving through space, but the space itself is stretching. Because between us and the distant galaxies, there is more space to stretch. And that is why they are moving faster away, because they just get stretched away from us more. Does that make sense? That's
correct. I've never heard that. Mm-hmm. So are they really moving, or is the space just pulling them?
The second one. Galaxies are moving. They are moving towards each other because of gravity. But when we talk about this expansion rate, it's not that the galaxies are traveling away from each other in space. It's that space itself gets bigger.
Got it. Okay. All right.
You may have heard the balloon analogy, where we say that the expansion of the universe is like a balloon being blown up.
Oh, that makes a lot of sense.
Okay, but actually,
oh boy.
Well, you said the surface. That's good. Because when people hear the balloon analogy, they think that it's like the inside of the balloon that represents the universe. They think that it's the volume getting bigger that explains the expansion, but that's not true. It's the surface of the balloon getting bigger that explains it. So not the volume, but the surface area of the balloon.
So if you wrote on it and blow it up, it's just things are just going to get bigger and bigger. Mm-hmm. All right. Oh,
yeah.
Dang.
What we're paying attention to isn't that the surface of the balloon gets further away from the center of the balloon. We are focusing on the fact that all of the latex in the surface of the balloon gets stretched.
Got you.
Mm-hmm. And in this analogy, dark energy is kind of like your breath that is making the surface of the balloon stretch.
Got it. That makes sense. Okay.
Good. Hello, fellow friends of the universe. Chris went to go examine a book on my bookshelf, and it turned out to be one of the ones that pulled him into an alternate dimension. Oh, darn. No, it's totally fine. It's one of the good alternate dimensions, and it's temporary. He's going to be back in just a couple of minutes, none the worse for wear, and I have some time to share a couple of messages with you. The first message is a recommendation of a brand new show here at Multitude called This Guy Sucked. This Guy Sucked is a history podcast for haters by haters. Join historian Dr. Claire Aubin and a new expert every week to pull back the scholarly curtain on some of the world's biggest bummers. From Charlemagne to Carl Schmitt, no dead person is safe, and the show's guests prove that the best part of understanding the past is criticizing it. New episodes come out every Thursday wherever you listen to your podcasts, so search for This Guy Sucked to learn about some truly awful people. Next, I want to say thank you to all of my patrons who support the show every single month. I really couldn't make Pale Blue Pod without you because this is an independent podcast. I don't have a company paying me to make this show. I don't have a big team of producers helping me choose guests or put things out every week. It's just me with help from Misha, my editor. Shout out to Misha. We love them. And some help from people at Multitude. So thank you all. And I want to give a huge special thank you to my sun-like stars, Scott Reynolds, Augustin, Tom T., Mark Mahoney, and Nicole Bartlett. You're all beautifully golden, and your gravitational field is the perfect strength to confuse people a little bit by warping the orbit of Mercury. So thank you for that. If you are not already one of my patrons, what are you waiting for? You can join this awesome group of people. You can hear your name on the show, make it to my patron star chart, and get research notes for most episodes by joining my Patreon for $5 per month. Brighter tiers like my Sun-like Stars get access to Pale Blue Pod at night, where I'm reading bedtime stories in what I hope is a slow and soothing voice. You can sign up now at patreon.com/palebluepod. I also offer annual memberships that give you a 13% discount across the entire year. That's 1 percentage point for every constellation in the sun's path across the sky. If you can't support the show financially right now, I totally understand. It's real out there, folks. A great way to help Pale Blue Pod grow is by word of mouth. Take a link to a specific episode and send it to someone who would enjoy it. That is the best, most effective way to help a podcast grow. And that's what I'm trying to do here, friends. I'm not trying to get rich with Pale Blue Pod. I just want to share the knowledge and familiarity of the universe with as many people as I can. So thank you for any help you can give me in that mission. All right, Chris has rematerialized on this plane of existence. I think it's time we get back to this conversation about dark energy. Okay, so that's what we learn from Edwin Hubble in 1929. At the same time, we were like, okay, sure, the universe is expanding, but surely it's gonna slow down, right? Like it can't just keep expanding forever. Apparently it can. In the 1990s, the Hubble Space Telescope, so not Hubble himself, he was gone by then, but the telescope that we named after him observed distant supernovae in really far away galaxies. And it found that those supernovae were fainter than we expected, which means that those galaxies are farther away than we expect. They're like farther away than Hubble's law says they should be.
Dang.
And we trust Hubble. We were like, no, Hubble's right. So that must mean that something in the universe is different. There must be something that Hubble just couldn't have seen. So what they determined was that the expansion of the universe is actually speeding up. So the distant parts of the universe are moving away faster than we expect, even though Hubble said the distant stuff is moving away faster. That was discovered in 1998. We were all alive. This is when they discovered dark energy. So dark energy is not just responsible for the expansion of the universe. That would have happened either way. Right. Dark energy is responsible for the accelerated expansion of the universe. Dark energy is what's making it speed up. The term itself, dark energy, was coined in 1998 by Dr. Michael Turner. He was a professor at University of Chicago, but he was at the time at a conference in Australia. So dark energy was coined in Australia as the driving force of acceleration.
Oh, okay.
So that's how we found it. That's like 100 years of history to get to the point we are now, where we know dark energy exists, but we don't know what it is. All we can really do is study its behavior at different points in the universe. So now I want to tell you a bit about what we have learned about dark energy and how it behaves. We have observed that it kind of acts as the opposite of gravity. So instead of mass attracting stuff to it, emptiness repels things away. So this is like the balloon analogy. If you have more latex in your balloon, then it can stretch bigger.
Okay.
We've also learned that dark energy only acts on large scales, like really, really big, bigger than galaxy clusters, because it doesn't overcome gravitational binding. So here in the Milky Way galaxy, dark energy is not making us expand. Even in our little local neighborhood of galaxies with like all of the 40 to 50 galaxies around us, dark energy is not going to take those things apart from each other.
Is it so it's only pulling on the fringes of our universe?
Yeah, it's only pulling like big groups of galaxies away from each other.
Is this a dumb way to look at it? All right, because the Big Bang, it's an explosion, right? So,
kind of. Yeah, that's how people talk about it.
So, but there's no air in space, because I look at an explosion, there's a concussion and there's a wave. Is the result of the Big Bang, and it just keeps going? Is that dumb to think? If
it's
there's
not dumb
nothing to
think.
stop it, there's no air. If there was an explosion, it's just going to keep going, right?
Right. That makes perfect intuitive sense, and that is what a lot of people thought for a very long time. That's still one of the possible explanations for dark energy.
Oh, that's right. No one really knows.
Exactly. Yeah.
Right,
so yeah. No, you're right on. But there are a few other ideas for what it could be, because we still haven't observed it in all of the different environments. Right? Like we need to collect more data before we can say anything for sure. But we do know that it only operates on those large scales. So it's like, in a way, weaker than gravity, right? Because gravity can still overcome it on these small scales. It does have this interesting effect where, because of the dark energy, because of the accelerated expansion of the universe, the edges of the universe are moving away from us faster than the speed of light. And there are individual galaxies that are technically being carried away from us faster than the speed of light, even though they individually are not moving faster than the speed of light, which is wild. It's wild because nothing can move faster than the speed of light except for, apparently, the expansion of the universe. Is your mind still intact?
That's crazy. Man.
My mind was blown after I read this. There's a galaxy called GNZ11. It's about 32 billion light years away. Keep in mind.
Insane.
Yeah. The universe isn't 14 billion years old yet. So it was carried away from us faster than that. And when we look at it, when we collect data from it, we are seeing this galaxy how it was very soon after it formed, 400 million years after the Big Bang. So we're going back more than 13 billion years when we look at this galaxy, and we can measure its speed, and we know that it is moving faster than the speed of light, like 400,000 kilometers per second.
And man, that's crazy. I can't even really. Yeah, that's wild. So it's dark energy. It's responsible for the expansion of the universe.
Mm-hmm. For the accelerated expansion.
The accelerated expansion of the universe. Mm-hmm. And it only works on extremely large scales. Mm-hmm. And it pulls on the... That's wild.
It's wild. I know. And we can see how strong it is in the universe. We see that it dominates the universe right now. It's like between 68 and 72% of the matter energy content of the universe. It's most of the universe, and we don't know what it is.
How have they tried to have they tried to like test it and find it? And
yeah, we're trying as much as we can, but we can't directly manipulate it.
And it doesn't react with anything?
Exactly. We can't influence it. We can't try to change it or run experiments on it. We can just observe it, which is really frustrating.
Man, that's
yeah.
The fact that people come up with this stuff is it blows my mind.
Mm-hmm. What blows my mind is how much we can learn about the very early universe. Because we know that dark energy is dominant now. We also know that it wasn't always dominant. Like, we can go back, and because we're looking back in time when we look at distant objects in space, we can understand what happened very soon after the Big Bang. So right after the Big Bang, there was this period of inflation where the universe ballooned from a tiny particle size up to, like a few thousand light years or something. Like it got really big. And then after that inflationary period, the dominant form of energy or matter in the universe was radiation energy. So the behavior of the universe was mostly influenced by photons and neutrinos, these very high energy, tiny little particles. From 47,000 years after the Big Bang, I love that we get this precise, to about 9 billion years after the Big Bang, matter dominated the universe. So it was dark matter and baryonic matter and their gravitational influence that kind of dominated the behavior of the universe. So it was harder for the universe to expand with all of that gravity trying to keep things together. And then about 5 billion years ago, something switched. Matter stopped being the dominant thing in the universe, and instead energy, specifically dark energy, became the dominant thing in the universe. So now the universe is expanding really fast, which means that we know the expansion rate of the universe has changed over time. Mm. But we do not know if the strength of dark energy has changed over time. Because if we know its effect has changed over time, but maybe it was the same strength. Mm-hmm. And other things just interacted with it differently. Or maybe dark energy itself changed strength over time. We're still trying to figure that out. And the answer to that question would tell us what dark energy is. We have 3 ideas right now. The first is that it's a fixed energy value. This is Einstein's cosmological constant, where the strength of dark energy is constant throughout time. The other idea is that dark energy its strength changes over time and in different parts of the universe. We call this quintessence. This is a fifth fundamental force. Proposed as the opposite of gravity. So instead of four fundamental forces, like the weak and strong nuclear force, the electromagnetic force, and gravity, we now have this fifth, which is quintessence. And kind of like gravity, how if you have more mass, you have stronger gravity. With quintessence, if you have more space, you have stronger dark energy.
Okay. Because, again, I'm not a scientist. I'm not educated in this, but it seems like... my mind just goes back to the Big Bang. It created whatever energy it created. It's not going to get any stronger or anything like that. It is what it is. And I felt like if it couldn't pull it when things were closer, I felt like even with people, you might not be able to pull like 500 pounds if you have it stacked up. But if you spread it out, it might be easier to pull. You know what I mean? So as a universe expanded, the weight is still there. It's just more spread out, and maybe it makes it easier to pull it. I know that might sound extremely dumb and rudimentary in my thinking, but that's just how I picture it in my mind. It's like all the weight is distributed. I wouldn't say evenly, but it's more spread out, and it's easier to bring along and drag. Would that make any sense at all?
That does make sense. Yes, okay. Astronomers talk a lot about the different density components of the universe when they're doing this type of work. I don't really talk about it that much because I think it gets into kind of complicated math and like weird geometry because you have to talk about the shape of the universe. But that is definitely a thing that we consider. As the universe has gotten bigger, the same amount of material is in it, but it's spread out more. So the density of the matter in the universe has gone down. And as the density of matter decreases, because the like content of the universe stays the same, the density of other things will increase.
That makes sense.
Yeah. So it is this interesting math balance problem that we do. But yeah, thinking of the density of material, like is it very smushed together or is it kind of spread apart through the universe? That is for sure a factor here.
Man, so have you ever been part of a research team that does stuff like this?
Not this directly. Although one of the ways that we can study dark energy is through the cosmic microwave background. Have you heard of this?
I have, but I couldn't tell you what it was anymore.
Okay. So the cosmic microwave background, or the CMB, is basically the heat signature left over from the Big Bang.
Okay.
So it tells us how matter and energy were distributed very soon after the Big Bang. Not immediately after, but like a few 100,000 years after the Big Bang. And we can study the tiny, tiny fluctuations in the cosmic microwave background and compare those to the large-scale structure of the universe now to see what has changed over time, because it gives us like a starting point and an ending point.
Okay.
I once did a project that tried to map the cosmic microwave background. It was an instrumentation project, so I worked with, I think, 3 other people, and we built an instrument, and then we collected data with it, and it was bad. It was bad because we built the instrument ourselves, but like it was mostly just to show us this is how you would go about an instrumentation project. So I did study the CMB, but we didn't apply it to dark energy.
Is the CMB almost like cut into a tree and like looking at the rings kind of? Or
Yeah. It's
you might see certain like elements present more during this time period.
Yes. Okay, so a tree ring, or like one of those geological layer surveys where you go deep.
Yes, that's a better one.
Yeah, so the CMB is like the bottommost layer of that soil column. Okay. And then we can look at other moments in the universe to get all of those different layers of time.
Right. That's so interesting. It seems like research in these areas will be frustrating because like I find it fascinating, but I always wonder like, okay, what do you do on a day-to-day basis when you're trying to, you're just doing a lot of reading, I guess, about other things?
Yeah, you're doing a lot of reading and a lot of data cleaning and analysis. So let me tell you about some of the projects that have tried to study this. So there are a few different methods broadly that you can take. One of them is studying the cosmic microwave background, so you get that beginning and end approach. Another approach is to get really accurate distances and velocities for as many galaxies as we can. This is like the Edwin Hubble method. There are a few different surveys and projects going on right now that use one method or the other, or a combination of the two of them. One of them is the Dark Energy Survey. This is based in Chile. I've actually been to the telescope that this instrument is on, and they collected data between 2013 and 2019 doing the first method, trying to get accurate distances to other galaxies and studying their distance and velocity. That ended in 2019, and we are still combing through the data of that. Like, they are still actively publishing papers because it takes years to go through this data. After the Dark Energy Survey kind of shut down and stopped taking data, another project came online in Arizona called the Dark Energy Spectroscopic Instrument. They came online in 2019. They had to pause for COVID, and then they started collecting data again in 2021. They are still collecting data. They're going to work for 5 or 6 years. That's the plan anyway. And they have done their first public release of their data, like in 2023. So when I say things in science move slowly, I'm talking on the order of years to not just collect the data, but to go through it, make sure that you're getting rid of all of the outlier data points that don't make any sense. You're trying to remove any sort of instrument bias, because these instruments, it's easier for them to see some things and harder for them to see others. So you have to correct for that. Right. And then just like individual people, once they get their data, it takes them a long time to familiarize themselves with it, come up with the code that will analyze it. Usually your analysis goes wrong several times. Like, I remember when I was in my PhD, if you were able to code a perfect analysis script the first time, sure, maybe a project would take a couple months, but you never get it right the first time because there are things in the data set you don't expect. There are just like coding bugs that you can't foresee. Right. So yeah, it's going to take a long time. Yeah, exactly. You get a value that the code's not used to.
For some reason you didn't plan for just like a 6th decimal place or something like that. And it's just like, I don't know how to handle that. Yeah.
Or there's like one missing comma in your code somewhere and it throws everything off.
Yeah, I can see that. This is very interesting, man. I feel I'm not upset at my life at all, but like just all the stuff that I was interested in as a kid, I really just didn't know that there were opportunities for jobs, like research and being a scientist in a lab. And I had no idea. I joined the freaking military, and looking back, that definitely was not the most ideal place for me, but it worked out for me. To hear of you doing work like this, going to Chile and, that's so cool. That's the kind of stuff I really would have been into when I was, 18, 19 in my early 20s. But man, this is really fascinating. I really appreciate you having me on here to listen to this stuff.
Oh, anytime.
I love it.
I love this. And you're so curious. It's really awesome to talk to you about it.
Oh, dang. I should go back to school, but I don't know. I don't want to be the 40-year-old guy in class with a bunch of like 20-year-olds asking questions when everybody don't want to leave.
No, there were 60-year-olds. There were 70-year-olds in my classes. I think you would be just fine.
Really?
If they don't think that your questions are interesting, that's a them problem. Because you are this whole episode, you've been asking fantastic questions. You've been connecting the concepts to your lived experience in really insightful ways. Like you have the perfect kind of curiosity about this. So if they don't want to be around that, then they shouldn't be in the program either.
Thank you. And I appreciate you. You also don't make me feel dumb for asking questions. Like if I think there's a connection somewhere and I'll ask, and you'll put me down gently if it's not, but it's not like, come on, buddy, what are you doing?
Yeah, no. Come on, buddy. I don't even know. That doesn't even sound authentic coming out of my mouth. Hey, pal.
Hey, bud. That's dad speak. Hey, buddy.
It is.
Yeah. So where they at right now with dark energy? Are they kind of still in the same spot? Any no big breakthroughs as of recently?
Exactly. We're still in the same exact spot. It seems like the static energy value and the variable energy value are just as likely. And until we can get a better map of the large-scale structure of the universe, and until we can better compare that to what the universe looked like in its early stages, we're not going to know about the long-term behavior of dark energy.
Right.
But we're going to learn. Astronomers are going to learn because they are very motivated to do that. We have more instruments coming on in the future, the Vera C. Rubin Observatory, and that's also going to be in Chile, and the Nancy Grace Roman Telescope, which will be launched into space. They're both going to try and figure out what dark energy is. That's one of their science goals. But we care about this because it will tell us about the history of the universe and like the current expansion of the universe, sure, but mostly because dark energy determines the ultimate fate of the universe. We don't know if the universe is going to continue expanding forever or if eventually it will start to slow down and then the universe will experience something called the big freeze or heat death, where everything just like cools down until there's no energy left. We don't know. And we won't know until we figure out how dark energy will act in the future.
I'm pretty sure there's people out there trying to figure out, can we harness this power somehow and make money off of it too? You know?
Oh, yeah. Chris, 100%. The repulsive power of dark energy, there are not even just sci-fi authors, but there are real scientists who are trying to figure out how that could be like a never-ending source of energy. Very similar to the people who are trying to make a miniature sun so that we have that never-ending fusion energy. But yeah, maybe one day.
Yeah, I love this stuff, man. This is so dope. God, I should have went to school for something different.
There is always more school to go back to.
I still have my GI Bill. You have no idea how many times I talked to my wife about it. I was like, I should go to Howard and be a scientist. I'm too old. Am I too old?
You're not. You are not too old.
Man, I can't. If I think about it too long, I will do it. It would be so cool to go to college and say I'm an astrophysicist. I
would be the first to write a letter of recommendation. Are you kidding me? You send in that app.
I really should think about going to school for science. I really should.
Or even just like auditing classes. Like you don't need, depending on what you want to do with it, if you don't want to work in a research field, you don't need to get the degree, but you're so interested in these topics that I think it'd be fun for you.
I wonder if I know every school is different, but do you think like science departments are open to people like asking questions? Because I'm here in Charlottesville where UVA is, and like I would love to sit down with like some scientists or astrophysicists and say, hey man, I would love to have them on my podcast or just come learn or be a helper. Like I think this stuff is so cool.
Absolutely. So you have UVA there. They have an astronomy department that you can tap into.
Really?
They have public talks. The thing you have in Charlottesville is the National Radio Astronomy Observatory base. And they do public talks most weeks that you can go into and listen.
What is it called? The
National Radio Astronomy Observatory. They're on UVA's campus. That's actually where I did my first research internship. They're like up a little hill behind UVA. Yeah.
Oh, okay. All right, I'm gonna call over. I'm gonna email somebody over there and figure out if I can meet some folks over there, have them on the podcast, and I think that would be really cool.
Yeah, they're really great. I'll send you some names after this because there are really good people at NRAO.
I want to check out the public talks too. I think that's really cool. One last question. You said they publish their research from these different locations. Like where can we find, where can I find that kind of stuff?
All of the different surveys, so like the Dark Energy Survey and the Dark Energy Spectroscopic Instrument, they have their own websites and
I can just Google
they
and find
put their publications there, yeah. I don't know if those papers are going to be as straightforwardly written as Edwin Hubble's. So if you don't want to read those papers themselves, I would recommend Astrobites. It's a group of mostly grad students who take a different research paper every day and they translate it into what a college student could undernd.
Oh, like plain, okay, that's cool.
Yeah.
I still like to see like the documents because I was an Intel guy and people are always like, you have a clearance. What does classified stuff look like? I'm like, you wouldn't even understand half of it. It would be boring if I left it out. So I do find stuff like this interesting, even though I wouldn't understand 90% of it. I just like to see what it looks like, just to take a peek at it. And it's just interesting that people dedicate their lives to this kind of stuff. And a lot of times it goes, people don't know who they are. but it's a lot of good research, and sometimes it really changes everyone's lives, and we never know who these people are behind the research, behind the numbers, and I think it's really freaking cool.
It is really freaking cool. I would love to see your name on a paper one day. Ooh. That would be so fun.
Yeah, right. That would be crazy. I am a published Intel author, though. So if you ever had any questions about radar sites in Africa,
oh yeah,
there you go.
Yes, actually, that's really interesting.
So that's very
what part of the radar did you do? Were you working on the instrument or the data side?
We worked on the data side. Basically, real quickly, we have air assets that fly around and we suck up all the RF from different countries. And basically, we take those radar signals, we digitize them, and we reverse engineer them, and we can tell you what type of radar is. Yeah, just on what we've got from the airplane, we can tell you that's a coastal surveillance radar, that's a surface-to-air missile, that's an air traffic control radar. And based on where all those things are, you can go, there's an airport there, there's this over here, this probably a military base here, they're probably doing this over here, just based on those signals. So we take those radar signals and also photographs that we get from different satellites and spy planes, and we just, like scientists, we verify our information. So if we get a bunch of certain type of radar signals from a certain location, we'll have a telescope go over there and take a couple pictures, and we match up those coordinates, look at the radar signals and the pictures, and go, based on the technical data, what we can find online, this is a blah 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 radar that's here. So that's basically what I did. It can be fun, but it can get kind of boring. Especially if you work in a country where we're not at war with them, or if they're not really a big, they're not big into defense. They might have a couple systems here and there, but if you're talking Russia, China, countries like that, it's hundreds of radars, and they're always doing new stuff. They're always digitizing stuff. They're always doing crazy new things when it comes to air warfare and stuff like that. So it's pretty fascinating if you get into the high level analysis. But
that sounds fascinating.
It could get boring.
Oh. I just like knowing things. I think that it would just tickle a little part in me to be like, oh, I know where the Chinese bases are.
Oh yeah, that's cool. Yeah, and knowing blind speeds of a radar and what type of aircraft these missile systems can defeat. And it's pretty interesting work.
Oh, so
this
cool.
is more fun.
Well, I think when you get into the practicalities of doing this type of research, it's honestly so tedious. It's right. Trying to get, the next decimal place in the value for the cosmological constant or something. I think that conceptually, cosmology is so fascinating.
Right.
Trying to understand how the universe formed and where it's going to go. One of the biggest, most interesting questions we could possibly ask and answer. But to do the work of answering it is, in my opinion, so mind-numbingly boring.
And hard, yeah.
And hard, yeah. So not my bag, but I'm glad there are people doing it.
Me too. Anybody in the science fields, people who come up with vaccines and all that kind of stuff, it's fascinating work. And it's wild seeing people who don't know what they're talking about tear it down, stuff like that. It's like, dude, come on, you don't know anything about vaccines. But anyway, I don't want to go there, but
so true. But
I
there's
appreciate
there to go.
You. Yeah. I appreciate you sharing your knowledge with me. This is a lot of fun. I would obviously love to come and do this again. So whatever you need a guest, I would love to come back on.
Fantastic. I love that. You're welcome back anytime, and I am serious when I say please reach out if you have questions for material for space jokes.
Space jokes?
Yes,
right.
please.
I'm working on about 10 minutes of space jokes. I might shoot you an email soon.
Yay! It would make my day to see that in my inbox for sure.
Really? All right. All right. I'll make sure I get some questions for you because I will be asking.
Good. Do you have any other questions about dark energy before we wrap up?
No, I feel like you really nailed it. I learned a lot, and I'll probably hop on YouTube and look up some more.
Yeah. Well, there's your evening.
Yeah.
Enjoy. Awesome. Right. I've loved talking to you again. It's so nice to have you in the office. Can you remind the listeners, since you've been here before, how they can find you online and let us know if you have any exciting work coming up?
Oh, yeah. You can find me on all things social media at Chris Allen Comedy, ALAN. I have a special that's out on YouTube right now, produced by my good friend Mark Norman. And April 5th, I got a kind of a big gig coming up. April 5th, I'll be at the Horseshoe Casino in Baltimore. So if you're in the Baltimore area, April 5th, Horseshoe Casino, 2 shows. I want to say 7 and 9. So I got coming up.
Awesome.
Yeah.
Check those out. If you're in the Baltimore area, go to this comedy show. And then also check out like the Space Telescope Science Institute. That's where the Hubble Space Telescope and the James Webb Space Telescope are operated.
Dang.
Yeah,
Yes.
Baltimore has cool science, cool astro stuff going on.
I will.
Okay, well, your links are in the show notes. So listeners, go follow those to follow Chris. And you asked so many great questions. So thank you for coming here today.
Thank you for having me, Dr. Moiya. I appreciate it. You have a great day.
Thank you. You too. And listeners, remember, no matter how dark your energy is, you're still space.
Ooh.
Pale Blue Pod is hosted by me, Dr. Moiya McTier, a.k.a. the universe's bestie. I created the show with original co-host Corinne Caputo, a comedienne extraordinaire, and help from the Multitude Productions team. Our theme music is by Evan Johnston, and our cover art is by Shay McMullen, and our audio editing is handled by the incomparable Misha Stanton. I am Go Astro Mo everywhere online, and you can stay in touch with the show and the universe by following Pale Blue Pod on Instagram or checking out our website, palebluepod.com. We are a member of Multitude, an independent podcast collective and production studio. So if you like Pale Blue Pod, you will love the other shows that live at multitude.productions. And if you want a shout out on the show and research notes for every episode, you can join our community over at patreon.com/palebluepod for just about $1 per episode. Thank you so much for listening to Pale Blue Pod. I'll be back next week. Bye.